must be run. So, first drop a line from C to a point D on the chain line so that CD is perpendicular to the chain line. Take the measurement of CD. After that, mark a point E on the chain line and erect a perpendicular at point F so that EF is equal to CD. Join C and F. The line CF runs parallel to the chain line AB. So, remember, to run a parallel line to a chain line through a given point, drop a perpendicular to the chain line from that point. Then, erect a perpendicular to another point of the same length from the chain line, joining. In this module, you have learnt that the basic problems in chaining are erecting a perpendicular from the chain line, dropping a perpendicular from a point to the chain, and running a parallel to the chain line through a given point. To erect a perpendicular point from a point on the chain line, follow the 3-4-5 method. The top of the right angle triangle is the perpendicular point. To drop a perpendicular from a point to the chain, mark equal lengths of line dory on either sides of the point on the chain line. Let's say you have to measure the horizontal distance between points A and B, which are separated by this hill. These stations are not intervisible because the hill is the obstacle to ranging. Note that there is no obstacle to chaining, as you can carry out stepping on the slopes of the hill. To overcome the hill as an obstacle, set stations C and D between A and B. Ranging between A and B is obstructed by the hill, but you can carry out stepping with the chain from A to the intermediate station C and from the intermediate station D to B. After that, add the horizontal distances of AC, CD and DB to obtain the distance between A and B. Now, take a look at the points M and N. There is a large rock between them, so ranging cannot be carried out. But you can run a chain along the horizontal from M towards N up to the point directly opposite N, which is O. After that, run the chain from N to O. In this way, you obtain a right angle triangle MNO. As MN is the hypotenuse of the triangle, you can calculate its length with the formula MN is equal to under root MO square plus ON square. So, now let's say you have to find out the distance between 2 points A and B with a building between those points. Here, the building is the obstacle to both ranging and chaining. Note that the building is an upright structure, so it is impossible to set intermediate survey stations or run a chain along its surface. So, you can set the cross staff at A and mark a point C so that line AC is perpendicular to line AB. After that, set the cross staff at C and mark a point D so that line CD is perpendicular to line AC. Note that you should mark D at a place beyond both the obstacle and point B. Set the cross staff at point B and mark a point E on line CD so that line BE is perpendicular to line CD. Now, you can see that AB is equal to CE. So, to know the distance between A and B, just measure the distance between C and E. So, remember, to overcome an obstacle to both chaining and ranging on a line, run 2 perpendicular lines of equal length, one before and one after the obstacle. After that, join those points and measure the length of the joining line. In this module, you have learnt how to solve the problems whenever obstacles occur in chain survey. To overcome obstacles to ranging but not chaining, you can use the chain for stepping or triangulation. To overcome obstacles to chaining but not ranging, first obtain two similar triangles. After that, calculate the distance by equating the ratio between the corresponding sides of the similar triangles. To overcome an obstacle to both chaining and ranging, mark points to get perpendicular lines before and after the obstacle. After that, join those points and measure the length of the joining line. The do's and don'ts in chain survey are basically a list of precautions to be taken in chain surveying. Let's find out what they are. Firstly, the surveyor and the leader should have complete and correct knowledge about chaining and the signals used for ranging. Otherwise, you cannot carry out chaining and ranging correctly and efficiently. Always erect ranging rods vertically. Do not leave them on the ground at an angle. Also, use colored flags on the top of ranging rods so that they are clearly visible. Otherwise, you will have difficulty in seeing the survey stations. Always use the correct technique of unfolding and folding the chain every time. Otherwise, the chain might get tangled and the links might also get stuck. Do not displace arrows from their correct positions. Otherwise, you will take measurements from wrong points on the ground. Always take the readings from the correct end of the chain. Otherwise, you will get incorrect measurements. Lastly, take care in reading and calling out the values of the measurements loudly and clearly. Otherwise, the measurements might not be recorded correctly.
1 meter.
1,
2 meters.
2 meters,
3 meter.
3,
4 meters.
4,
5 meters.
5.
So, remember, always follow these do's and don'ts in chain surveying to ensure that you get the best results from your survey. In this module, you have learned the do's and don'ts that need to be followed in chain surveying. The surveyor and the leader should have complete and correct knowledge about chaining and the signals used for ranging. Erect ranging rods vertically with colored flags. Use the correct technique of unfolding and folding the chain and take readings correctly and call them out loudly and clearly. Do not displace arrows from their positions and do not count chain lengths incorrectly.
We have already seen the parts of the prismatic compass. Before you can use a prismatic compass for survey operations, you must make some temporary adjustments to it. The step-by-step procedure to adjust the prismatic compass is as follows. Fixing the compass to a tripod. Centering the compass. Leveling the compass. Adjusting the prism. Observation of bearings. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the legs of the tripod. Place the prismatic compass on the threaded top of the tripod. Now, turn the compass box clockwise to fix it to the threaded top. Determine the center of the prismatic compass by either dropping a piece of stone from the bottom of the compass box to the ground, or suspending a plumb bob from below the compass box to the ground. Now, level the prismatic compass by using the ball and socket arrangement provided on top of the tripod. Loosen this arrangement and place the box in such a way that the graduated ring should rotate freely without touching either the bottom of the box or the glass. Move the prism up and down till you can see the figures on the graduated ring sharply and clearly. Finally, bisect the ranging rod at the required station perfectly by sighting through the prism slit and horsehair at the sight vane. In this module, you have learned to apply the temporary adjustments to the prismatic compass. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the tripod legs. Center the prismatic compass by either dropping a piece of stone from the bottom of the compass box to the ground, or by suspending the plumb bob. Level the prismatic compass by using the ball and socket arrangement provided on the top of the tripod. Move the prism up and down till you can see the figures on the graduated ring sharply and clearly. Finally, bisect the ranging rod at the required station perfectly by sighting through the prism slit and horsehair at the sight vane. In this module, you have learned to apply the temporary adjustments to the prismatic compass. Firstly, adjust the tripod to a suitable height for observation by spreading and contracting the tripod legs. Center the prismatic compass by either dropping a piece of stone. You have seen that the direction of a survey line can be shown with respect to other survey lines or with respect to a fixed meridian. You also know that if the directions are shown with respect to a meridian, then they are shown on the map or plan with bearings as the measurement. Let us suppose you have a map or plan that shows the measurements of all survey lines only in terms of bearings, whereas you require knowing the measurement in angles. How would you compute the angles from bearings? Let us find out the answer by going through this module. Welcome! After computing this module, you will be able to compute angles from bearings. Take a look at this area. As you can see, there are 4 main stations. When this area is shown in the form of a map or a plan, this is how it looks. The 4 main stations are marked with the letters A, B, C and D. Note that the point N on the map is not a main station, but the magnetic north of the area. We know the bearings from the magnetic north to every survey line within the area, as we have already calculated them with the help of the compass. So now, let us start computing the angles based on the measurement of the bearings. To begin with, let us find out angle AOB. We can say that angle AOB is equal to the difference between bearing OB and bearing OA. Note that these bearings are in fact the arms of the angle AOB. From the diagram, we can see that bearing OB is equal to 132 degrees, 30 minutes, and that bearing OA is equal to 50 degrees, 30 minutes. Therefore, we can say that angle AOB is equal to 82 degrees, 30 minutes. Similarly, if we have to find out angle BOC, we can say that it is equal to the difference between bearing OC and bearing OB. From the diagram, we can see that bearing OC is equal to 232 degrees, 30 minutes, and that bearing OB is equal to 132 degrees, 30 minutes. Therefore, we can say that angle BOC is equal to 100 degrees. Similarly, we can say that angle COD, which is the difference between bearing OD and bearing OC, is equal to 87 degrees, 30 minutes. But angle DOA has to be calculated in a different manner, because it is in a different quadrant after the whole circle bearing. So to calculate angle DOA, you have to use the formula. Angle DOA is equal to 360 degrees minus bearing OD plus bearing OA. So angle DOA is equal to 360 degrees minus 320 degrees, 30 minutes plus 50 degrees, 30 minutes, which is equal to 90 degrees. To check whether the angles calculated from the bearings are correct, you must add them up and see whether they add up to 360. So let us add angle AOB, angle BOC, angle COD and angle DOA. This is equal to 82 degrees, 30 minutes plus 100 degrees plus 87 degrees, 30 minutes plus 90 degrees. As this sum is equal to 360 degrees, we can say that the angles computed from the bearings are all correct. So remember, this is the procedure for computation of angles from bearings. In this module, you have learnt how to calculate angles from bearings. To calculate angles from bearings, calculate the difference in the bearings forming the arms of the angle. To calculate an angle from a bearing in a different quadrant after the whole circle bearing, subtract the bearing measurement from 360 degrees and add the measurement of the complementary bearing to the difference. You have seen how to compute angles from bearings while carrying out the survey of a site using a compass. Now, let us say you have a map or a plan which shows measurements of the included angles between successive survey lines and the measured bearing of the initial survey line. Based on these data, if you are required to calculate the bearings of the subsequent survey lines, how would you do it? Let us find out the answer by going through this module. Welcome! After completing this module, you will be able to compute. Let us begin by taking a closer look at the map. A, B, C and D are the included angles which have been measured clockwise from the respective backstations. Theta 1 is the measured bearing of the survey line MN. We know that the bearing at the initial survey line MN is theta 1 and that the first included angle is A. We can calculate the bearing of the next survey line. NO with this formula, bearing NO, that is, theta 2 is equal to the theta 1 plus A minus 180 degrees. Similarly, the bearing of the next survey line OP, that is theta 3, is equal to theta 2 plus B minus 180 degrees. In the same way, the bearing of the next survey line PQ, that is theta 4, is equal to theta 3 plus C minus 180 degrees. However, to compute the bearing of the survey line QR, that is theta 5, we have to use the formula theta 4 plus D plus 180 degrees. 180 degrees are added rather than subtracted to compute the bearing of a line whose included angle is not measured from the meridian from which the bearings are to be computed. As you can see, the included angle D has not been measured from the meridian at Q. It has been measured with reference to the survey line QR. So remember, in this module, you have learnt how to calculate bearings from angles. To calculate bearings from angles, add the included angles to the bearing of the preceding line. If the sum is greater than 180 degrees, subtract 180 degrees. If the sum is forebearing means the bearing of a line as measured in the direction in which the survey progresses. Back bearing means the bearing of a line measured in the direction opposite to the survey. For example, in the figure A, B, C, D, E, where the survey progresses clockwise from A to E, theta is the forebearing of the survey line AB and θ1 is the back bearing of that very line regarded as line BA. Note that in the whole circle bearing system, the difference between the back bearing and forebearing must be equal to 180 degrees. So, in the example we have seen above, the forebearing of line AB is 55 degrees and the back bearing of line BA is 235 degrees, 180 degrees more than the forebearing. So, in this module, you have learnt the concepts of fore and back bearing. Forebearing means the bearing of a line as measured in the direction in which the survey progresses. Back bearing means the bearing of a line measured in the direction opposite to the survey. The relation between forebearing and back bearing is that back bearing is equal to forebearing plus or minus 180 degrees. You have seen that the compass is a useful instrument for calculating bearings. Interestingly, the compass can also be used along with a tape or chain for a type of survey called traversing. So, what is traversing and why is it important? Let us find out in this module. Applications of compass survey in the field. After completing this module, you will be able to explain the importance of traverse in surveying and perform the compass traverse adjustments. Often in surveying, irregularly shaped ground features such as ponds or lakes, or rivers or roads need to be surveyed. To do so, you should run a series of survey lines along or around the outline of these ground features so that you obtain the correct framework of the survey. As such lines typically run in a zigzag pattern, the compass, along with the chain or the tape, help you to take accurate measurements of their varying directions and lengths. This type of survey, in which several connected survey lines of known direction and length form the framework, is called traversing. You have just seen that you can depict the irregularly shaped ground features like lakes, rivers or roads with the help of traversing. When the connected survey lines form a loop or a polygon around the ground feature, as in the case of a pond, it is called a close traverse. When the connected lines form an unjoined pair along the ground feature, as in the case of a river or a road, it is called an open traverse. Often, when a closed traverse is plotted based on measurements taken in the field, the end of the last survey line of the traverse does not exactly meet the starting point of the traverse. This error is called the closing error. It occurs due to errors in measuring distances and angles on the ground.
सुप्रभात, नमस्कार। आप सभी दर्शकों का बहुत बहुत धन्यवाद जो हमारे साथ इस कार्यक्रम में जुड़े हैं। मैं भगवती जमनाल,
मैं दिव्यांशी चौहान आपका CSE रूबरू कड़ी में स्वागत करते हैं। इस श्रृंखला में हम हर बार आपके सामने CSE द्वारा प्रदान की जा रही सेवाओं से रूबरू कराएंगे